So looks like our visitor brought with him two gifts of Providence. We have a longer day because of him, and we have sunny, warm weather because of him. Even though he came all the way from Chicago, which we know the winters are so much better. So it's a great honor for our department to welcome Mike Turner, who is the director of the Kavli Institute of Cosmological Physics at the University of Chicago. Mike is famous since I've known him in my last, 30 years as a student. Oh, no, actually 20, maybe 25 years. As a student, going all the way throughout my career, as being famous for being a great football player. There's a great football player named Michael Turner that played for the Falcons, and we got the wrong guy. But actually, Mike was also famous for his humor. And so, in a good payback, I'm going to have to say a few things about him. So Mike did his undergraduate at Caltech, where he took a one-on-one course with Richard Feynman, your claim to fame. Then he did his PhD at Stanford, went on to Chicago, did his postdocs there, and continued on as a faculty, where during that time, in the early 80s, remember the cosmic microwave background radiation, the fluctuations which confirm the seeds of structure in our universe, was done in the late 80s, but in 1983, Mike Turner, Paul Steinhardt, and not Stephen Hawking, but you corrected the calculation of Stephen Hawking. In 1983, Steinhardt, Bardeen, and Turner calculated the prediction of the density perturbations in the cosmic microwave background radiation, which were confirmed in the late 80s by Kobe. He's done numerous other things as well. He coined the term dark energy and really pushed for the community to make sense of this, both theoretically and experimentally. And let's say the last thing about Mike that really, I think, for me, the most important thing was when I was a young, hungry and desperate graduate student, lacking any direction in my career, Mike Turner was, at the time, the assistant director of the National Science Foundation, and clearly, an important guy, what have you. And he came to a meeting at the National Society of Black Physicists, where I had attended, and was very generous with his time to encourage us and take our questions seriously. On that note, thanks for coming, Mike.
Thank you very much, Stefan, for the kind introduction. Now I have this dilemma. Oh, the lights can go down of which screen to point at. But I bet every speaker has had that dilemma. So the past 30 years has seen stunning progress in our understanding of the universe. So we know it's held together by the gravity of mysterious dark matter. It's accelerated. The expansion of the universe today is accelerating due to the repulsive gravity of dark energy, which is even more mysterious. And we believe it underwent a burst of early expansion, which we call inflation, which took quantum fluctuations on subatomic scales and blew them up to astrophysical scales, and they became the seeds for all the structure that we see today, which is probably the deepest connection between the very big and the very small. So this is going to be a bit of a philosophical, oh, I hope nobody leaves. It'll also be fun. So what have we learned? What can we hope to learn, and how can we put this all together? And I've had a fantastic day, and I think the highlight was with the graduate students who helped me prepare this talk. They generously donated their time, and they asked me, what the hell did that abstract mean? And so I'm going to do a much better job. So how we choose to describe the universe, or whatever system you're studying, determines the questions you ask and ultimately what you can learn. And so my title is, how many numbers, which quantities do you use to describe the universe? That's really what I'm trying to get at. And why would you have such a talk? Well, at its core, cosmology is different than other science. So in physics, you do an experiment. You set up the experiment, you take data, you infer something about nature. The last thing you would ever want is that the result of your experiment depends upon the names, ages, and heights of your graduate students, right? You prepare, you get rid of the initial conditions. And it could well be, in cosmology, Murray Gell-Mann used to call cosmology an environmental science, where we're looking at its weather, we're looking at climate. It could well be that the state of the universe today depends upon the initial conditions. And it could well be that all we ever learn is how it evolved, and maybe glimpse those initial conditions. So that makes cosmology a little bit different, and it makes this question about how many numbers. I was really pleased that everybody read my abstract and didn't like the 0. Did I say 0 was the answer? I can't remember what I said. Anyway, I like that everybody read the abstract, and 0 is the answer. Okay, so let's take a step back to a simpler time. Right. So until 1980, this is something Stefan was alluding to, cosmology was really the sole province of astronomers. So it didn't involve physicists. So it was a different time. And let's go way back. 500 years ago, the universe was really simple. Physicists like to simplify, right? Spherical cows and all of that. It was just the solar system. And if I did my research right, we didn't have Neptune, Uranus. Of course, we don't have Pluto today. Well, we have Pluto, but it's different than what we thought. Things were a lot simpler. And Johannes Kepler had an explanation for the universe, which is the solar system. And so some of you will recognize these as nested, at least Jim does, as nested platonic solids. And so that gave the ratio of the orbits. And so you just need one number. You need to know where did the AU come from. So it's a one-number universe. Okay, let's see. Let's move up to the 1970s. And boy, those were the fun days of astronomy. There were about maybe 10 cosmologists in the world. And some people are probably thinking, maybe even the chair of your department, boy, I wish we could go back to those days where we didn't have to have any cosmologists in our department. Alan Rex Sandage, who was a student of Hubble's, was the second most famous astronomer of the 20th century. Really, all kidding aside, a great man. And he said that cosmology was a search for 2 numbers. Just 2 numbers. That's all we need to know. And those 2 numbers, and here he's standing next to the 200-inch telescope on Mount Palomar, and that instrument was going to figure out cosmology. It was going to measure those 2 numbers, and probably there's a handful of people who know the 2 numbers. QNOT, so the expansion rate, and QNOT. I had fun with the graduate students. Only one graduate student knew what the deceleration parameter was. Actually, she got the sign wrong. But that's fine because, here's the universe is expanding from the Big Bang, and the expansion rate is the slope. And 1 over the slope gives you the h. So that's pretty important. And I used to think h0 was not that important, but it's the number 1 parameter in all of cosmology. The second one is how is the universe slowing down, the deceleration parameter. So minus the acceleration, the droopiness parameter, and Sandage hoped by measuring QNOT that one could figure out, are we slowing down enough for recollapse, or is the slowdown not very much at all and we will expand forever, or is it the Goldilocks? So those were the 2 numbers. That was cosmology in circa 1970. So we've actually measured h0. This is a fun chart because, one of the things you learn in the political world is if you've got bad news, you tell it. Don't let the audience tell it. don't let the audience say, oh, they couldn't even measure H0, you know. So it started out at 600, and we've wrestled it into submission at 73. We'll come back to this, somewhere around 73, and we even put error bars on it now. And so Wendy Friedman led the Hubble Key project and used the Hubble Space Telescope to do it. Adam Reiss, Nobel Prize winner, has played a role in this. But we really, this most important parameter has been measured to a couple of percent, although we'll come back to it. It's still extremely interesting. QNOT has just disappeared. And a couple of years ago, I wrote a paper with an undergraduate beyond QNOT and H0, cosmology is no longer just two numbers. But what's most interesting here is we showed that QNOT could not be measured with both accuracy and precision. So it's not even measurable. And everyone loves to complain about referees. And I don't know that the referee's in the audience. But so not so many people read this paper, but at least one astronomer learned the difference between precision and accuracy, because in the paper he asked that we define them because he didn't understand. I don't get this, you know. Accuracy, precision, it's the same thing. Anyway, so QNOT, the joking aside, QNOT is not measurable. It's not a measurable quantity, and you can ask me later. It's not. We have more interesting things to talk about it. So then Stefan alluded to this. The current era of astronomy began somewhere in the 1980s, and we like to call it the Chicago School. And we have a provost who said, you know, it's not bragging if it's true. So, but I'll leave that to you. And the key ingredient that got injected in all of this is that there are deep connections between the very big, that's cosmology, and the very small, elementary particles. And this is a view graph from my mentor, David Schramm, who is really, I keep this in nitrogen. This is an amazing transparency that it still exists. We held the first meeting that brought together particle physicists and astronomers at Fermilab. And the idea was that the early phases of the universe, when it was just quark soup, really, they're not just pedantically interesting. They lay down the blueprint for the rest of the history of the universe. And often these changes in looking at a subject, the vocabulary gets changed. And I'm actually thinking about the work of Michael Kosterlitz and his colleagues, who changed the language of condensed matter physics from, you know, gas, liquid. I don't want to say the names because I'm going to embarrass myself in front of so many distinguished condensed matter physics, but introduced a new idea. And so the words are different. So it's dark matter, it's inflation, it's dark energy, it's quark soup, it's cold dark matter. So a whole different way of looking at it, describing it, and a different set of questions. Okay, and so here is the complete history of the universe. Time runs this way, so we start with quark soup. This is where some really interesting things happen. I mentioned inflation earlier, I'll come back to it. The origin of matter, the origin of dark matter. So actually, I'm teaching a class and the word emergence just came to mind. So we start with this hot, formless soup, and layer upon layer of structure emerge. First neutrons and protons, and then the universe was a nuclear reactor when it was seconds old, and we call that Big Bang nucleosynthesis. That's where the helium was made. And then atoms formed, and when atoms form, the universe becomes transparent to the radiation. And so this is the microwave background that we see. It comes to us at last scattered with material in the universe when the universe was about 400,000 years old. And so the known history of the universe starts at 10 to the minus 5 seconds, maybe a bit earlier with inflation. But we really, this has been a tremendous accomplishment. So that's right. How many numbers does it take? So today, unlike Sandage's time where he struggled to get 2 numbers, we got a whole list of numbers here. There's the temperature of the microwave, and look at, they've got really small error bars. the age of the universe, the omega parameter, H0, actually we'll come back to why there's two different values, the number of neutrino species, the tilt, there's a whole bunch, I won't go through all of them, but there's a whole bunch of, the list just goes on and on. So which are the relevant parameters to be talking about? Which are the relevant ones to measure? And when you measure them, what do they mean? So a lot of what we understand about the universe comes from the microwave background. The microwave background, so I blew up the last little bit of the universe. As you look out in space, you look back in time. And you know, maybe these are the most distant quasars that you can see, and then we hope to see the first stars, and then it's the dark ages. And then when the universe was about 1,000 times smaller, and it was about 400,000 years old, that's where the universe underwent the transition from ionized matter to neutral matter, and that's where the radiation in the universe last scattered. It then was redshifted to microwaves, and when we look at the cosmic microwave background, we're looking at the physicist's universe. So we're looking at a universe that was very simple. No stars, no galaxies, spherical cow. So, I mean, it was very homogeneous. And this is what we see. So I bet a lot of people here recognize this as the Planck satellite's map of the cosmic microwave background. So this is the cosmic microwave background in false color. Red is hot, blue is cold. The dynamic range here is a part in 10 to the 5. So the universe back then was smoother than a ball bearing that you get from the Ball brothers. Actually, I don't know if the Ball brothers make ball bearings, but somebody must make ball bearings very smooth. And let's see. Where it's hot, there's more matter. Where it's cool, there's less matter. This is a map of the distribution of matter in the universe. This is kind of a cosmic Rosetta Stone. From this, we can learn a lot about the universe. And that we learn so much about the universe from this shows you how smart cosmologists are. We just stare at this map, and we're able to see the age of the universe. We're able to see how much matter there is in the universe. Actually, that was a joke. I'm just kidding about that. So the best picture we have is from the Planck satellite. I have the world's best T-shirt collection. This is one I just added. So this is from the Ariane launch site in French Guiana. This is a rare T-shirt, and I'm willing to sell it later today. And so the remarkable thing from Planck is that you can fit this pattern of hot and cold spots with just 6 numbers. So, 6 is the answer then. And so the person who introduced these 6 numbers is George Astacio. He was responsible led the team that did a lot of the analysis. And here is the multipole power spectrum. So this is multipole number L, and this is temperature difference for the different multipoles. If you think in terms of angles, this is big angles and small angles. So these are the temperature differences. So the way we really learn about the microwave background is not by staring at that, what basically is Gaussian random noise, but taking the multipole transform, and you'll notice that a series of acoustic peaks pop up because the ordinary matter, the baryons, was trying to fall into the dark matter potential wells and getting pushed out by photons. And so this is really the response function of the universe when it was 400,000 years old. And there's a whole bunch of data points here. It goes out to multipoles beyond 2,500. And 6 numbers give you the curve that fits all of this. And those 6 numbers, as I'll say, is motivated by a theory. So what are the numbers? The density of ordinary matter, or baryons. The total matter density. So you might say, well, aren't those the same? No, that's the dark matter problem. This number is 5%. That number, the total baryon, total matter density is 30%. They differ by 50 sigma, meaning that there's something else out there. That's the cold dark matter. The amplitude of the lumpiness of the density perturbations. So that's one of the fitting parameters. The index of the power spectrum that tells you how those perturbations vary from scale to scale. The sound horizon, which is roughly the more, you can think about it as the age of the universe, or what is the physical scale associated with this sound wave, and then the optical depth. So this is a term that astronomers are very comfortable with, but physicists are not used to. So that's what is the chance that a microwave photon scattered. I told you it was last scattering at 400,000 years, but actually there's a chance that a photon would hit some hot gas along a free electron along the way, and that's called, that chance is about 6%. And this is so precise that you have to put that in. So those are the 6 numbers. And so they aren't 6 random numbers, but I'm going to plant the seed. Are they the best 6 numbers? Okay. So they're motivated by and assume the lambda CDM cosmology. And probably many of you have heard that. And I guess I didn't utter the words yet. But our present paradigm has, let me start at the bottom, dark matter. So the gravity of dark matter particles that we don't know what they are hold together all structures in the universe, and it's their gravity that built all the structures. Dark energy. So the universe is, the expansion of the universe is speeding up. QNOT is negative. And our default for understanding the cause of this is lambda, or the cosmological constant, which is mathematically equivalent to quantum vacuum energy. And then this early burst of expansion, inflation, which I'll talk a little bit more later, which gave us the smooth, uncurved universe. So the universe is uncurved with the seeds for galaxies. And these seeds for galaxies came from quantum fluctuations. So going back to the parameters, so matter was one of the parameters. Dark energy wasn't, but matter plus dark energy gives you the critical density. So I've written kind of a heuristic equation here. So the density perturbations, their amplitude and their tilt, so that describes these density perturbations. And the cold dark matter is the matter minus the baryons. So the parameters that you saw over here, so baryon density, matter density, density perturbation amplitude, and tilt, are related to the underlying framework. Okay, let's now for some other views. So here's someone, the most famous astronomer in the world, I believe, Lord Reiss of Ludlow, wrote a book saying just 6 numbers to get our universe, to determine our universe. So what were his 6 numbers? 3, the Trinity. So 3 dimensions of space. And he argues that if you live in a universe with more than 3 dimensions, life is not interesting. Of course, we know, actually a lot of people in this audience know, 2 dimensions is really interesting in condensed matter physics. But he picked 3. Weak gravity. So in order to get stars to live a long time, gravity has to be 36 orders of magnitude weaker than the electromagnetic force. Boy, these 6 look very different. Well, let's go down to the bottom. Density perturbation, so that's the same one that we had earlier. Small lambda, that is, we don't want too big a cosmological constant, because if we had too big a cosmological constant, the universe would have started accelerating earlier before galaxies formed. A flat universe, so an uncurved universe, that's our universe. And look at this one, that the energy released when 4 protons fuse to form helium is 7% of the mass. Wow. Okay, the number is 6. So Michael Rowan Robinson also wrote a book, The 9 Numbers of the Cosmos. Now, I'm going to point out something. This shows you, if you're a lord, you're a lot smarter, or you're 50% smarter. So Michael Rowan Robinson is not a lord. I don't even think he's a sir. I don't even think he's a knight. And it took him 9 But again, baryon density, cold dark matter density, hot dark matter density. So some of the dark matter is neutrinos. Lambda, everybody likes lambda. The CMB anisotropy, that's what I showed you earlier. The temperature of the universe, that's the, when I teach an introductory cosmology course, I tell the students, one number that you have to memorize is the temperature of the microwave background, 2.7255. So we have a quiz, and I say, okay, last chance to get it right. If you don't get it right, I got the tattoo artist here, and it goes on your forehead. We can do that at Chicago. I don't know if you can do that at Brown, but at Chicago, we can do tattooing. The age of the universe, the Hubble constant, and the star formation history. Interesting, interesting. Murray-Gell-Mann, some people in the audience, raise your hand if you've heard of Murray-Gell-Mann. So, good, I'm pleased that extremely influential scientist. So he believed that there is a unique theory of everything. I'm going to call it the toe. I don't like the term the toe, but it makes the PowerPoint slides tidier. So he thought it was a string theory, and that there is only one string theory that works. And so I'm going to come to, did God have a choice with the laws of physics? And Murray would say no. And the rest is weather. Actually, once you pick that, the rest is just happens. It's just you're done. It happens. And you can't really describe individual particles. Yeah.
What about the spring tension?
You'll have to take that up with Murray. Actually, no, that's a good question. Somebody, if I don't answer it in 5 minutes, feel free to leave. Actually, he actually said environmental science, but so another point of view, this is, did God have a choice about the laws of physics? So Einstein asked this question, not in the letter that he sent. This is his famous God letter that just got sold for $250,000. It was not in here. So actually what's sort of interesting, the reason I put this here is Gell-Mann would, at one point, actually I should never speak for Murray, but at one point Murray did think that there was a unique string theory, that God would not have had, I don't think he would have put it that way, but there would be no choice. There was only one logically consistent. Martin Reiss, in this book, I think, he was really, I'll come back to the multiverse. I think he was basically saying he tried them all, and we just got the ones that we got because we're here to observe them. Oh, the A word. So Harlan Hawking also weigh in at 0. So the Harlan Hawking wave function of the universe determines the initial state of the universe, and the initial state is specified by the theory of everything. So it's just a path integral over the Hamiltonian. So 0, that's it. That's the initial state of the universe, and the rest is just environmental science. Are you getting a feel for where we're going here? Okay, different approaches. And again, the reason that this is interesting is it gives you an insight into where we are in cosmology, where we're hoping to go, what is the right, everybody knows this. The hardest part is asking the right question. Once you ask the question, it's basically over. It's just, you hire a bunch of experimentalists. You got to explain it to them 2 or 3 times because they tend to be slow, but you heard the secondary laugh there. That was the experimentalists. They got the joke a little later than the theorists. Okay, no more experimentalist jokes. So, so the different approach is 0. So there's some unifying physical, I didn't call it the toe here, and that is all that's needed, period. That's it. That's all you need. So this, the middle ground is descriptive. So it was kind of Kepler, it was Sandage, it was Planck. So we're going to describe the universe we see, largely theory agnostic, but it's kind of informed by, we got a solar system. And then at the far end, or I don't know if I have ends here yet. So is the anthropic and the multiverse. So the dice got rolled a lot. The dice got rolled a lot. And implicit in that is a lot of times it wasn't very interesting. You've seen pictures of the multiverse, right? So different pieces of the universe have different laws of physics, and most of them are completely boring. There's no stable particles. It's just empty. It's dark. And then there's ours, and then there's the really good ones. And so basically what you're doing is trying to infer from first principles, or not from first principles, but from logic and what we see, what was needed to get us. So it's, in fact, I should have called this reverse engineering. It's basically reverse engineering. Here's what we got. How did we get there? Okay. Oh, right, the narcissistic principle. That's a better name for it. Okay. So I want to pause again before we, get into the home stretch here. So this is very impressive. That's, no matter how you count it, it's thousands of numbers, and a theory with 6 parameters fits them all. I remember before the microwave background, we were bragging about what the microwave background would do. A bunch of astronomers said, oh my God, with four numbers you can fit anything. And I said, that's not my worry. My worry, I mean, first of all, we have more than four numbers, but my worry is that with just 6 numbers, we won't be able to fit that many data points. So that's a truly impressive achievement, but where do we go next? What does all of this mean? So let's see, stunning achievement. Let's look at those 6 numbers. 4 of them are pretty much descriptive. Matter density, baryon density, age of the universe, optical depth. It's just describing what you see. 2 of them kind of are getting at physics, the amplitude of the density perturbations and the tilt. And so I would say we should aspire to do better. Of course, that's what you always tell people, aspire to do better. And what I like to tell my students is, we spend a lot of time talking about what is science, what is the scientific method. So science is more than just a book of facts. It's understanding. And you've heard the Eddington quote. Have you all heard the Eddington quote? No experimental fact should be believed until confirmed by theory. And that's because science is more than just a book of facts. It's understanding. And so sometimes if there's some discovery that you can't understand. Okay. Oh, now comes the University of Chicago part of this. So we could have spent the whole time on the first slide, but so what was the question? So how many numbers does it take to determine our universe? So we parse that. And first of all, let's see, how many numbers? So we're looking for a real integer. Well, I don't know, are there mathematicians here? We could, a quaternion or an imaginary. So we're looking for a real integer here to determine our universe. Well, what we're really talking about, we don't mean the position of all the particles and that we got a galaxy here and we got Earth and we got Pluto and we couldn't figure out if it was a planet. So what we mean are the most important features and statistical properties, not the position of every particle. Okay, and that now you can kind of see why Murray calls this an environmental science, or it's more like climate. So there are 2 extreme limits, and I'm going to tell you which one I take here. So one is just purely descriptive. And so now I'm back to what I said before we started, which is it's all about learning how the universe began. It's all about how learning the universe began, is that if you think about it, you could imagine that the state of the universe today depended critically upon the initial conditions. And at the end of the day, all you can do is kind of run the movie backwards. So that would be one point of view. The extreme opposite, let's see, I called it purely deterministic. Actually, this is not my typing. This was one of the graduate students. I don't like that purely deterministic, but you get the idea. It is all a consequence of the theory of everything and the laws of physics. So everything was automatic. So basically, nothing was left to nothing was left to chance. Let me just say that. So it had to come out this way. So I call this the self-booting universe, the automatic universe. So the goal, this is where the zero comes from, is that once you have the laws of physics, the rest just follows. That's a really extreme point of view. It maybe means that cosmology, at the end of the day, if those particle theorists were smart and could actually figure out what the theory of everything is, then all we'd have to do is just figuring out the story of the universe. And if you ask astronomers what cosmology is all about, often they'll say it's about the story of the universe. How did we get here? And actually, that's a pretty good answer. Okay, so let's see if I put a little more meats on this. The laws of physics, not initial conditions or parameters, determine the present large-scale features of the universe. So I'm not talking about the weather, I'm talking about the climate. So I'm not talking about whether we have Earth here or not, but just that there are planets and stars. And I'm agnostic to the uniqueness of the toe, so I don't need to know that. I don't need to know who the watchmaker was, or, God forbid, we live in a multiverse. I'm agnostic to, there's just some controlling theory that does it all, and the rest is automatic. So this might sound really boring. But it's not really boring because we don't know what the toe is. And so by studying the universe and looking at it this way, it might give us insight about the theory of everything. Okay, important caveat. Somebody asked, did he already leave? About the parameters. He didn't, okay. So the parameters of the toe, if any, do not count. I'm only talking about cosmological parameters. Somebody handed me the toe. That's somebody else's job to do the how many toes you have. Although I thought you had 2 toes, but I could be wrong. Only cosmological parameters count, and I'm saying the goal is 0. And so I'm thinking that we want a universe that doesn't depend upon initial data. How have we done so far? This is called the successes, and of course, yeah, actually brown is where the easy graders are, right? So I count partial successes. Showing up at class counts as a success. So Big Bang nucleosynthesis, that's the first home run. So before the microwave background was discovered, Hoyle and Taylor, let's see, do I have this? Hoyle and Taylor, I'll go back to that. Hoyle and Taylor discovered that in the most primordial samples of the universe, it was 24% helium, 25% helium. So you could have said, I guess the universe began with 25% helium. That's what we figured out. So this period when the universe was a nuclear reactor, you don't have to specify the initial chemical abundances. Nuclear physics plus the expansion of the universe does it, guaranteed. So it's not an initial condition. Structure formation. So the fact that we have galaxies and superclusters and all those things, clusters of galaxies, once you specify the initial inhomogeneity, gravity and the expansion of the universe, and if you're really interested in stars, hydrodynamics does it all. There's nothing else to do. There's nothing more to learn. Inflation, we'll talk about that. So inflation really was the big one. I'll come back to that in a second. It was when it came around 1980, and it's when we really started thinking differently about cosmology, that we want to free ourselves from the initial conditions. Particularly, the microwave background shows that we live in a very smooth universe. And then, sadly, I won't have that much to talk about the amount of atoms in the universe. So that's an important number. That was one of Planck's numbers. How many atoms are there? We think that came about from an excess of matter over antimatter developing due to the non-conservation of baryon number. Actually, I'll put it up there on a t-shirt, so it's even been on a t-shirt. The non-conservation of baryon number, CP violation, and the expansion of the universe. So this is an idea that goes back to a t-shirt salesman That's before the ITP got its K in 1981. Okay, nucleosynthesis. I was telling the students about this. It all started with a wrong paper. And I was telling them how important wrong papers can be. In fact, Wolfgang Pauli got it right. So the biggest insult Pauli could give you is, your paper isn't even wrong. And I think what he meant was it's trivially right. 2 + 2 = 4, I'm not interested. 2 + 2 = 5, I'm interested. And I mentioned Hoyle and Taylor finding the large, so actually this paper didn't have a correct equation. He was really describing the R process for the astronomers in the audience. And yeah, I'm going to just skip the rest of this one. Inflation. So this goes back to 1970 and the time of Sandage. So the question was, if you start the universe with some initial geometry, so we're thinking general relativity, how likely are you to get our universe? Or put another way, there's all the initial geometries. It's a dartboard on that wall over there. The creator throws a dart. How likely is it that you get our universe? And it's not very likely. So what Hawking and his graduate student Collins showed is that if you start with the initial geometry, you get a mess in a jiffy. A jiffy being 10 to the minus 43 seconds, for those of you who are not familiar with that unit. So it's not a logical inconsistency. If you start with a very smooth space-time, you can get our universe. And so this was the dilemma of initial conditions. And this is a really interesting problem. So Roger Penrose, who I'm sure most of you have heard of, thinks that there are theorems about the initial conditions, that there are only certain kinds of initial conditions that are allowed. Another point of view is inflation. And the point of view of inflation is that if the universe underwent a tremendous burst of expansion, a small, smooth piece could become really big enough for everything that we see. It's driven by the false vacuum energy of a scalar field, and when that scalar field vacuum energy decays, that produces the heat in the universe. So it's automatic. It's automatic. And not only that, the quantum fluctuations in that field give you the lumpiness. So that's in the self-booting. You don't have to start with smooth space-time. The universe could begin like this, and a small piece of it would develop into what we see. Okay. Dark matter, because I know you guys are interested in dark matter. So here's another bit of the self-booting universe that, whether or not it works, we'll have to see, is, you remember the quark soup? So in the quark soup, there's all the particles that they haven't produced yet at the LHC, because it was the most powerful accelerator. And so if there were dark matter particles, they were there in great abundance with their antiparticle. As the universe cools, those particles want to annihilate, because once the temperature is lower than their rest mass, they can no longer be made. And if, because of the expansion of the universe, eventually they get far enough away from one another that they can no longer annihilate, and they're left with a relic abundance here. So here's their abundance relative to photons. They're left with a relic abundance like that. And so here's a more careful calculation. This is really interesting. There's some religious implications here, because the abundance is higher the weaker the force. So the meek shall inherit the universe. And for this annihilation cross-section, 3 × 10 to the minus 26 centimeter cubed per second, so that's sigma v, you get the right abundance. And so if you work out the cross-section, that is the cross-section for a weak interaction process. And that was the name WIMP was born. So automatically we get this. Now, I'm just going to pause here because it's not clear that this is really going to work. There'll be people in the audience who says that doesn't work. But this, again, falls into it was guaranteed. We didn't have to put in dark matter. It's a relic from the early universe. Okay, in the absence of the toe, what do? We don't have the toe. Well, as I said earlier, that is a feature, not a bug. If we had the toe, then we would just be doing, we would just be climatologists, doing climate models. So descriptive parameters can lead to discoveries, disruption, and a portal to the toe. So I'll mention a few examples where we try to use things that we could measure to figure out what the theory is. And oh, here's my advertisement against them. So here are you remember the sirens in Greek mythology? And look at these poor sailors being, so we do not want to be seduced by the sirens of the multiverse. We don't want to just say things are the way they are, because if they weren't that way, we wouldn't be here to figure it out. Okay, so how can we make progress? So let me give you a trivial example of how you can learn from parameters that you would say were really just descriptive. So we know the temperature of the microwave background. It's all, for those of you who haven't memorized it, it will be tattooed to your forehead. We know the age of the universe. Both are just telling us today. Okay, we have the Friedman equation that can relate them. If we assume that the universe only had radiation in it, which is a stupid assumption because we know there's matter, but let me just, as a pretend example, assume that, so here's the Hubble parameter, the age of the universe is 1 over, here's the Hubble parameter, there's the age of the universe. You can solve for T0, I know you're smart. So it's 1/2 h0 to the -1. So we plug in the formula for black body radiation, we figure out the age of the universe. If there were only radiation, the universe should be 984 gigayears old. But it's only 13.8. So if you just look at the equations, that must mean there's more energy density, and in fact about 1,000 times more than is in radiation. And so we would have deduced that there's matter in the universe. Now, I know the experimentalists are thinking, this guy is as stupid as most theorists who come and give us a colloquium. We already know there's matter. We're made of matter. So I was just trying to say, if you make accurate measurements, you might learn something. So that's back to the Hubble constant. So Wendy Friedman and Adam Reiss, using good old-fashioned methods of measuring the distances to objects and their redshifts, get this number, 73.5 plus or minus 1/2. The microwave background allows us to infer the Hubble constant. And you get 67.4 plus or minus 1/2. And you might say, this is good enough for government work. Those are close enough. They differ by more than 3 sigma. So could they both be right? I mean, obviously one could be wrong. That's the simple solution. Could they both be right? Using the microwave so this is the data. So here's the microwave background. Here's the direct measurements. So there have been improvement in precision, and the discrepancy has gotten bigger. Could they both be right? Yes, because the microwave background assumes lambda CDM. So again, taking one descriptive parameter and measuring it 2 different ways reveals something about the underlying theory. And this is where I work in gravity waves. We have a new way of measuring distance to check this measurement using gravitational radiation. And that first event of 2 coalescing neutron stars already gave us a value that lies nicely in between those 2. I'll skip those. So measuring things with precision is a really big deal. So the microwave background, we talked about that. Big Bang nucleosynthesis. So we understand that very well. The amount of deuterium and helium that results from that pins down things that are going on in the universe. Here's some other things. Some opportunities on the horizon. So inflation. So we understand inflation in terms of the potential of a scalar field. And here is that tilt index. Inflation also produces gravitational waves. And the level of gravitational waves that might be detected not with LIGO, but in the microwave background, depends upon the potential. So we have these parameters to measure that can give us a hint about whether or not this automatic universe is right, and some hints about what the toe is. Let's see, I'll skip that. How many people in the audience know who that is? Well, I guess you can read that it's Steven Weinberg. And I noticed this when I was preparing this talk for the first time I gave it. Do you have any advice to offer the next generation? So I figured, yeah, sure, I'm willing to listen to Steve Weinberg. Winston Churchill had a motto at the beginning of World War II, keep buggering on. In that spirit, I think it's better to do something than to do nothing. My advice is to try crazy ideas and innovative experiments. Something will come up. So be bold, I think what he was saying. I'm going to skip that one. And I'm going to finish up with 2 slides here. So so have I convinced you that it's the automatic universe? What could possibly go wrong? What could possibly go wrong? So initial conditions might matter. I'll do Penrose first. So it could be, he's a pretty smart guy. Could be that there are rules about the initial singularity, that the watchmaker didn't have a choice. Or for those of you who know about axions, this one is much more disturbing to me. So if the axion particle is the dark matter, it's produced in a really funny way. It's produced from the misalignment of a scalar field from the minimum of its potential, and the dark matter is just that scalar field oscillating back and forth. So a zero mode. Okay, so what's wrong with that? Oh, well, its energy density depends upon where you started it. And where you started it is a random variable. And so there's something that depends upon someone rolling the dice. So you might say, well, that's kind of a small thing, but there might be others. And then the limits of cosmology. So cosmology is different. The universe is really big. Historically, the universe has often been beyond the reach of our biggest ideas and most powerful instruments. George Ellis, a well-known and important cosmologist, has pointed out something that's obvious but deep. We're limited by the knowledge of our past light cone. And so the first question that students always want to ask you is, how big is the universe? And you tell them, well, I can't answer that. All I can tell you is how big the observable universe is. And then there are some iron curtains. The CMB, the universe is opaque earlier than that. Well, neutrinos might take us to 1 second, so the last scattering surface for neutrinos is 1 second. Here's the worst iron curtain. So let's suppose you buy inflation. If you buy inflation, then, the whole point of it was to make you insensitive to what the universe looked like before then. So that's it. And then testability in a historical science. So what constitutes the proof of inflation or the proof of dark matter? So in fact, let me start with a really easy one. The proof of, Big Bang nucleosynthesis. How do we really know that happened? Well, we take general relativity, nuclear physics measured in the lab, calculate abundances, measure them, they check. So we complete the circle. So most cosmologists, I hate to use the word believe, but I think we have it really happened. What about dark matter? So dark matter, this is my dream. I call it closing the circle. So we've got these dark matter particles. This is why I really love the neutralino. So we get it 3 different ways. We produce it at the LHC, and Greg brings us a bottle of them, and we put it right here on the table. We detect the particles in our halo because the dark matter particles in our halo interact with an underground detector called xenon. Oh no, I guess it's supposed to be LZ. Or is it Lux? I can't remember. LZ. Rick's not here, it doesn't matter. He doesn't show up. It's xenon that detected it, and you can tell him I said that. And then they annihilate in our halo, and you see gamma rays. So then I think you'd be able to convince someone from Missouri. Remember Missouri, that's the show me state. So show me. I think even someone from Missouri would believe that most of the matter in the universe is something that we're not made out of. Okay, the last two things, technology, hard and soft. Let's see. So this is my fun part. This is the neuroscience part of the talk. I have talked to neuroscientists, and I've asked them, why can't a dog understand quantum mechanics? Does anybody know the answer to that? We probably don't have any neuros. No prefrontal lobe. So that's where all the abstraction happens. So can we understand the universe? Well, we have a prefrontal lobe, but it's, okay. Sorry?
What about AI, artificial intelligence?
Well, there you go. So that's why we need people smarter than me here. So maybe it'll be a computer that explains, except, that computer that learned how to play chess won't share any of its secrets. So the hard technology part you understand. We can't build good enough instruments. Okay. And we're also assuming objective reality. So the simplest version, although there is a test for this, so I'll give you the test for this. So the simplest version of the universe is, it's just me. In fact, it's not even my body. It's just my brain, and I'm imagining all of you. Okay, there is no objective reality. Did you know you can disprove that? The way I can disprove it is, if that were the case, I would have won a Nobel Prize already. Okay, there we go. So I hope you've enjoyed this tour. It's supposed to give you an insight into where we are in cosmology. We know a lot. We'd like to understand a heck of a lot more. And we're trying to figure out, at the end of the day, how much can we learn about the universe? I know we can learn a whole lot more. I don't know what the limit is. Thank you very much.
Some questions?
Well, first of all, Michael, thank you. I have two questions. One of them, it was touched upon in your talk, which was that we have the cosmic microwave background, which is a curtain, and then you talked about the neutrino sphere, which is a curtain. But what is understood about the limits of what I like to call sonoastronomy, namely gravitational wave astronomy, which we will be developing in the next couple of decades? What's the limit on how far back that might get us? That's one question. And the other question is, you talked about the fact that when we look at the CMB, basically 6 numbers describe massive numbers of observed data points. The only other theory I can think that's sort of like that is the standard model, where the number of parameters is much larger, but the numbers of understood observed data points is very, very much larger than in CMB. So could you contrast those two things? Those are my two questions.
Yeah, so let me do the first question, which was easier. So gravitational waves, if you ask where is their surface of last scattering, you of course know the answer, which is actually we don't really know the answer, but the standard answer we tell people is the Planck epoch. And so gravitational waves, if inflation is right, gravitational waves were produced during inflation. I asked the graduate students if they knew about the BICEPT experiment, which thought it had seen evidence for the gravitational waves. It's a fantastic experiment, by the way. It thought it had seen evidence for gravitational waves from inflation. It didn't. It didn't meet the Sagan, extraordinary claims require extraordinary proof. That would have taken us back to 10 to the minus 38 seconds. Our current limit is about 1 second, which is the elements made in the hot Big Bang. So the compare and contrast. So the standard model of particle physics is truly one of the great intellectual achievements of the last century. It's the culmination of a guy on the island of Miletus, or whatever the hell the island was, asking a simple question. The guy was Democritus, and what is stuff made out of? And it took 2,500 years to answer that question. and we think we know what it is, and it really is a fundamental theory. I mean, and the particle theorists here could say that, yes, it's an effective field theory, but it's well-controlled approximations, and we can really, the reason I'm choking on this and emphasizing it is it's a real theory. And now you go and measure things, and they agree. And there's a couple of anomalies, but actually they wish there were more anomalies. And so it's a little bit different on the cosmological side. So we have this fantastic lambda CDM fits the data, but it's not really a fundamental theory because we don't know what the dark matter is. We don't know what lambda is. And let me come back to the 6 numbers. In fact, I was talking to Savas about this. So let's suppose the theory was almost right. I don't know what the hell that means, but let's suppose it's almost right. So I have 6 knobs that I can turn to fit the data. So, in fact, let's suppose the theory were totally wrong. Anytime I am curve fitting, all the students know this, anytime I'm curve fitting, I can tune the knobs to get the best fit to the curve. And I can label the knobs anything I want, you know, the height of Jim Gates. I can, you know, whatever I want to do. That doesn't mean it's really measuring your height. And so these knobs may not be measuring what we think they are, because we may not have the underlying theory is not a fundamental theory, and it may not be the right theory. And so now you're saying, boy, you're going 5 sigma British on us here. So let me rein that one in. And the Hubble constant could be the first indication that we're turning the knobs on the wrong theory. So we've got 6 knobs. It's pretty close, but it's not quite the right knobs. And so lambda CDM, the CMB is telling us H0 is 67. Gosh, Wendy Friedman, she's a great colleague. She's really good. She says 73. And that discrepancy could be that we're using the wrong underlying theory. So I think there is the difference. We don't have anything, I'm not even sure that anyone would call it an effective theory. It's certainly not a fundamental theory. It's a pretty good theory. It in not very many words and equations summarizes the universe that we find it. In fact, I went to a wonderful conference celebrating the 75th anniversary of the birth or death of Lemaitre, so one of the fathers of cosmology. And the title of my talk was Lambda CDM, much more than we expected, now much less than we want. So scientists are greedy. So no one in cosmology in 1980 would have ever imagined that we would be where we are today. And those of us who were there then now say, but we want more. Scientists are greedy. We really, the more, it's like where's Savas? It's the mouse and the cookie. It's why you don't give a mouse a cookie. Did you know all that? Everybody know that book? She knows that book. Why don't you give a mouse a cookie?
Because then he'll want a glass of milk.
Yeah, and then what happens? Yeah, then it's a napkin, then it's another cookie. And so it's been an amazing success. It's allowed us to ask new questions, but we can see that we're still not, the questions are not, we want more.
If no one wants to ask a question, I want to come back to a point that was raised back here.
Oh, well, yeah.
That is, in the fundamental theory, it was asked, what about the string tension? And so if you would riff on that for a while, I'd appreciate it.
I'm not going to riff on that because I'm a cosmologist. I'm a dumb cosmologist, and I'm just taking, so that comes back to something that we don't want to talk about, which is where did the laws of physics come from? And because we don't know. And I think that's why Martin Reiss loves the multiverse, is they all got tried. And so we really don't know. I mean, when I tell my students, I say, there could be, I don't know, there could be a prime mover, there could be a God, or it could be that we're just an experiment in a freshman physics lab in a very advanced civilization, and it was the D student. We just honestly, we don't know why. Why? Yeah. That's why I didn't want. Yes.
Assist.
So I'm just a lowly idiot first year, so please forgive my.
But still smarter than me.
Okay. So I sort of want to push back against your rejection of the whole multiverse thing on the grounds of the history of astronomy and our understanding of our place in the universe has gone from, you know, we are the only thing that exists to we are a special thing. We are, you know, basically a series of revelations that we are less and less and less special than we actually thought. So what fits that paradigm better than our universe isn't special, it's just one of 10 to the 100 universes?
So I'm never going to debate you about this because you're too good at this. So what I think your argument is the argument I call no one ever made money betting against the universe being bigger than we think it is. Did I say that right? Got a bunch of You're just saying don't bet against the universe being bigger than we think it is because history. So that is right. I think if I were giving a talk about, or if I were debating the multiverse, what I would say is the multiverse gives me a headache. Why does it give me a headache? It gives me a headache because it may be the most important idea since Copernicus. Yeah, Copernicus had a pretty good idea. But it's not testable.
Right.
And so our brand is, you know, we're not the only company in town. Our brand is we tell you how the universe works. We don't tell you how we think it should work. We don't tell you who runs the universe. We don't tell you who invented the universe. Our brand is we tell you how the universe works. We're really good at it. We're unbelievably good at it, but we don't do why. And we don't do, you know, could there be, you know, if we took the most beautiful universe, I'd be up here talking about the steady state. So beautiful theories are killed by ugly experimental facts. And that's the nature of science. Bob, did you want to ask? Oh, I'm sorry. Go ahead.
Okay, the question is, you showed in one of your plots the result of using. You showed in one of your plots the result of using the gravitational detection of the two neutron star events as a measurement of the Hubble parameter, and you had on the same plot the two present reigning measurements of it. And this is a completely different technique.
Completely different.
That's different than both of them, but with just one event, of course.
It doesn't. It's not.
But it comes
definitive.
in the middle. There was this very lovely article by your colleague Holtz that was in Physics Today about using the two neutron star events in the future. Do you see that it will ever approach the kind of precision that the CMB experiment gets? I mean, it needs to have other LIGO-type detectors because you have to determine the plane in which you have to determine the polarization.
So it's a brand new technique, and you know this. Actually, I've gone to so many visionary lectures that you gave about detecting dark matter. And so you get a new idea, and it's going to measure things better than anyone has ever measured. And, you know, it's 0.01%. And then somebody says, oh, yeah, oh, well, it'll be 0.1% at least. And then, oh, new effect. Oh, it'll be 1%. But hope springs eternal, and having a different method is always important. And I think that, you know, right now we're on a sugar high with the gravity waves because, you know, no one ever thought they'd be detected. And all of a sudden we have 11 events. And so in astronomy, the astronomers have a rule. Once you have 10 events, it's astronomy. So now gravity waves are astronomy. And so I think there's a good chance that they will do it. And of course, that only checks the direct method. It doesn't mean that the microwave background is wrong or right. So there could be error on that side. But having a new way, having a cross-check is always important. And I think gravity waves are just a new window on the universe, and we'll see how fast that window develops. But so far, it's been very exciting. And you know, if they got 67, yeah.
I'm a condensed matter experimentalist, so I'd like to ask from an experimental perspective. So imagine I'm looking at your CMB picture, and you use this 6 parameters to fit.
Yeah.
Let's say ideally, if one can play God, can do this experiment a few times, how much variation you might expect in this color map? In other words, if I take your color map and then tell a graduate student to pixelate all the whole map and then randomize it and then run the code again to get the 6 parameters, do I get the same thing?
The short answer is yes. Let me come to the map.
That's very alarming, isn't it?
Well, see, the parameters measure, let me get the biggest version I can of the map. Where did I, there's a pretty big version of the map. So first of all, the one feature I don't think you'll get next time is Stephen Hawking's initials, SH, right there. So this comes back to what we're trying to do, what the goal of determining the universe. So we're trying to determine its statistical properties. And so according to inflation, at least the simplest models of inflation, this map is Gaussian random noise. And so the multipoles are completely uninteresting, but their variance, so the average value of any multipole is 0. It's its variance that the theory specifies. So the variance of the multipoles is related to the underlying physical parameters. So if we threw the dice again with the same underlying physical parameters, then when we analyze the sky, we should not see Stephen Hawking's initials. We should not see the same, you know, if you find, oh, there are features that people can find in it. You won't see those, but you should get the same parameters because the theory specifies the variance of each and every multipole. And I think I answered your question. So the answer is you'd get the same values because all we're determining is the statistical properties. So if you ask, would you get the same multipoles? Oh, maybe that's what you're asking. You will not get the same multipoles. So you will not get the same, you know, 5 quadrupole moments. They'll be very different. But their variance, well, again, the variance won't be exactly the same, but if you analyze all of the variances, you'll get the same underlying parameters.
Thank you.
One more question? Okay. Let's thank the speaker.
Thanks. You know the mouse and the cookie.
Many times, yes. Dad would be proud of you.
It's
Take your mic now too.
right. Thank you.